Hello, and this time digital gates level 3, the harder ones. Fill in the truth table for this circuit. Well, this is a NOR gate followed by an inverter. And a NOR gate followed by an inverter is just an OR gate. And an OR gate gives you a 1 when any of its inputs are 1s. These are just buffers, they have no effect on the logic at all. So we're going to get a 1 here when any of these inputs is a 1. In fact, the only time we get a 0 is when A, B, and C are all 0. Then the output of the NOR gate would be a 1, and the output of the inverter here would be a 0. All of the rest of the time, it's 1. Next. Very similar, except we've now got an inverter in B. Reminder again, it's a NOR gate followed by an inverter, so it works like an OR gate, and the only time you get a 0 out of an OR gate is when all three inputs are 0. And that would only happen when A is 0, B is 1, so that B inverted is 0, and C is 0. So that's this row here. A is 0, B is 1, C is 0. Then you'd get a 0. Every other time, you'd get a 1. You double click for 1, single click for 0. You can toggle between them. There are some different types of ones. This is just careful working through the logic. If A is 0, then this point here must be a 1. And B is 0, this is a XOR gate, and the two inputs are different. This is a 1, this is a 0, so this will be a 1. C is 0, so this point here will be a 1. D is 0, so this point here will be a 1. So all three inputs to this NOR gate are a 1. And if all three inputs to a NOR gate are a 1, then the output must be 0. In fact, if any input to a NOR gate is 1, the output is 0, so I didn't really need to consider C and D at all. Anyway. Another one of the fun design ones, but this is actually quite an easy one because this, you can possibly immediately see, is a 3-input AND gate. And we can get one of those from down here. Then all I need to do is wire it up like so, and I'm done. 84%, really quick. I was a bit lucky with that. So with circuits like this, we just need to carefully work through them. A and a B, so the two inputs into here are both 1s. This is an AND gate, so the output here must also be a 1. This is a buffer, which makes no difference at all, so this point here, I'll get a different colour for this, is also 1. Right. Here we've got a AND gate with a 1 and a 0 going into it, so that's a 0 at that point in the circuit here. And this is 1 going through an inverter, so we've got a 0 here. This is an XNOR gate, which gives you a 1 when its inputs are the same. So that would be a 1 as well. So we've got two 1s going into a NOR gate, which means the answer should be 0. Because any 1 going into a NOR gate would result in a 0 coming out. So the answer would be just 0. And one we have to work out the input state. Well, this is a NAND gate. And a NAND gate only gives you a 0 when all three of its inputs are a 1, so B must be a 1. Easy. Output here, we just have to work through the circuit again. In fact, there's a shortcut. This is a 3-input OR gate. This is a 1. If a 1 goes into an OR gate, the output will be a 1. It doesn't matter what the two other inputs in. If any of the inputs into an OR gate is 1, the output will be a 1. So without thinking about it too much, without considering this logic up here at all, I can say that the output will be a 1. I'll just do one more. Circuit 1, but actually not a difficult circuit 1, because if you look at that, you might be able to see it's a NAND gate. All I need to do is pick a 3-input NAND gate, and I'm away. You don't need to wire it up neatly, it's just me being a little bit overzealous. Right, Sometimes they get a little bit harder and you need to put inverters in here, but this one, fairly straightforward. Okay, hopefully you've got the idea. Oh, I should mention again, if you want to delete a wire, you right-click on it. If you want to delete a component, just pick it up and drag it off the screen like that. That should work fine. I think that's all you need to do. Good luck.